How to build LLMs from scratch, the complete 6-step guide. Introduction, demystifying LLM development. Building large language models from scratch might seem like magic reserved for tech giants, but it's actually a systematic, well-defined process. Here is the details of distilled over 1,000 pages of research into 6 essential steps that make every future discussion about LLMs instantly clear and meaningful. This comprehensive guide will show you exactly where technologies like web scraping, tokenization, RLHF, transformer architectures, ONNX optimizations, and dozens of other technical components fit into the LLM development pipeline. By the end, you'll understand not just what these technologies do, but when and why they're used in the journey from raw text to intelligent AI. Step 1. Data collection, the foundation of intelligence. Web scraping and data gathering. Everything begins with data, vast amounts of it. Modern LLMs are trained on datasets containing hundreds of billions of tokens collected from diverse sources across the internet. This isn't simply downloading files, it's a sophisticated extraction process. Web scraping technologies. Scrapy and Beautiful Soup crawl websites systematically, extracting text from HTML while preserving structure. Selenium handles dynamic content and JavaScript-heavy sites that static scrapers cannot access. APIs provide structured access to platforms like Reddit, GitHub, and academic databases. Data sources include books and literature, Project Gutenberg and digitized libraries, research papers and academic publications, Wikipedia and educational content, code repositories, GitHub and GitLab, forums and discussion platforms, Reddit and Stack Overflow, news articles and journalism, web pages and blogs. Filtering and cleaning. Quality over quantity. Raw web data is messy, biased, and often inappropriate for training. This stage involves aggressive filtering. Technical cleaning. Remove duplicates using hash-spaced deduplication. Strip broken HTML, malformed text, and encoding errors. Filter out spam, advertisements, and low-quality content. Content filtering. Remove copyrighted material to avoid legal issues. Filter biased, toxic, or inappropriate content. Apply language detection to ensure data quality. Remove personally identifiable information, PII. Dataset structuring. The cleaned data gets structured with metadata including source URLs, timestamps, quality ratings, and topic classifications. This metadata becomes crucial for later filtering and analysis. Step 2. Pre-processing and tokenization. Converting text to numbers. The tokenization challenge. Computers cannot understand text directly. They need numbers. Tokenization converts human-readable text into numerical tokens that models can process. This seemingly simple step is actually quite sophisticated. Tokenization methods. Bi-pair encoding, BPE, used by GPT models, starts with individual characters and iteratively merges the most frequent pairs, creating a vocabulary that balances common words with rare subword components. Sentence piece. Google's approach treats text as raw byte sequences, handling multiple languages and scripts more effectively. Unigram, a probabilistic approach that optimizes vocabulary based on likelihood maximization. Data formatting for training. The tokenized data gets structured into training-friendly formats. JSON for human-readable configuration and metadata. TF record for TensorFlow-based training pipelines. Hugging Face datasets for compatibility with popular ML frameworks. Sharding splits massive datasets into manageable chunks for parallel processing. Key pre-processing steps. Sequence length normalization, typically 2048 or 4096 tokens. Padding and truncation to create uniform batch sizes. Creation of attention masks for variable length sequences. Step 3. Model architecture and pre-training. Building the brain. Architecture selection. This is where we define the model's fundamental capabilities. The choice of architecture determines everything from the model's reasoning abilities to its computational requirements. Popular architectures. GPT, generative pre-trained transformer, decoder-only architecture optimized for text generation. T5, text-to-text transfer transformer, encoder-decoder architecture treating all tasks as text-to-text. Llama, Meta's efficiency-focused architecture with innovations like RMS norm and SWI-GLO. Falcon, optimized for training efficiency with high-quality datasets. Parameter scale decisions. Models range from 7B parameters for edge deployment to 175B plus for maximum capability.
Each parameter requires 4 bytes in FP32, so a 175B model needs 700 gigabytes just to store weights. Compute infrastructure. Training large models requires massive computational resources. Hardware. A100 and H100 GPUs, NVIDIA's flagship training accelerators. TPU V4 or V5, Google's specialized tensor processing units. Multi-node clusters, often requiring hundreds or thousands of GPUs. Software stack. PyTorch, Facebook's flexible deep learning framework. JAX, Google's NumPy-compatible library for high-performance ML. DeepSpeed, Microsoft's optimization library for large model training. Megatron LM, NVIDIA's framework for training massive transformer models. Pre-training process. Causal language modeling, CLM. The model learns to predict the next token given previous context. This simple objective teaches the model grammar, facts, reasoning patterns, and world knowledge. Training optimizations. Cross-entropy loss measures prediction accuracy across the vocabulary. Gradient checkpointing trades computation for memory by recomputing activations. Parallelization strategies. FSDP, fully sharded data parallel, distributes model parameters across GPUs. Zero redundancy optimizer eliminates memory redundancy in distributed training. Efficiency techniques. Mixed precision, FP16, BF16, uses 16-bit floats to reduce memory usage and increase speed. Gradient clipping prevents exploding gradients that can destabilize training. Adaptive learning rate schedulers automatically adjust learning rates based on training progress. Step 4. Model alignment, teaching the model to be helpful and safe. Supervised fine-tuning, SFT. Raw pre-trained models can generate text, but they don't follow instructions well or maintain helpful conversation patterns. SFT addresses this by training on carefully curated datasets of high-quality interactions. Key datasets. Instruct GPT datasets, OpenAI's instruction-following examples. Alpaca, Stanford's instruction-following dataset. DALL-E, Databricks' high-quality instruction dataset. Reinforcement learning from human feedback, RLHF. This sophisticated process aligns model behavior with human preferences. The RLHF pipeline. 1. Response generation. The model generates multiple responses to prompts. 2. Human ranking. Human evaluators rank responses by quality, helpfulness, and safety. 3. Reward model training. A separate neural network learns to predict human preferences. 4. Policy optimization. The main model is refined using proximal policy optimization, PPO, to maximize predicted human satisfaction. Safety and constitutional AI. RLAIF, reinforcement learning from AI feedback, uses AI systems to provide feedback, scaling beyond human evaluation. Adversarial training. Deliberately test the model with challenging prompts to improve robustness. Bias filtering. Systematic removal of unfair or discriminatory behaviors. Step 5. Deployment and optimization, making models production ready. Compression and quantization. Even smaller LLMs are too large for most production environments. Compression techniques reduce model size while preserving performance. Quantization methods. GPTQ, post-training quantization that maintains accuracy while reducing precision. AWQ, activation-aware weight quantization, focuses on preserving important weights. LLM.8b converts models to 8-bit integers for significant memory savings. Knowledge distillation trains smaller student models to mimic larger teacher models. API serving and scaling infrastructure. Production LLMs must handle thousands of concurrent requests with low latency. Serving technologies. VLLM, optimized inference engine with paged attention for memory efficiency. Triton Inference Server, NVIDIA's scalable inference platform. TensorRT, GPU optimized inference accelerations. ONNX, cross-platform model format for deployment flexibility. RayServe, distributed serving for ML models. Monitoring and continuous learning. Production systems require constant oversight. Performance tracking. Monitor response quality, latency, and throughput. Hallucination detection. Identify when models generate false information. Usage analytics. Understand user patterns and model performance. Continuous improvement. Regular model updates based on production data. Step 6. Evaluation and benchmarking, measuring success. Performance testing suites. LLMs must be rigorously evaluated across multiple dimensions. Code understanding. Human eval measures programming ability through code generation tasks. General knowledge. MMLU, Massive Multitask Language Understanding, tests knowledge across 57 academic subjects. ARC, AI2 Reasoning Challenge, focuses on scientific reasoning. Comprehensive evaluation. HELM, Holistic Evaluation of Language Models, Stanford's Comprehensive Evaluation Framework. OpenAI Evals, Extensible Evaluation Framework for various capabilities. MT-Bench, Multi-Turn Conversation Evaluation. Evaluation dimensions. Accuracy, factual correctness of responses. Helpfulness, practical value to users. Harmlessness, safety and ethical behavior. Honesty, acknowledgement of uncertainty and limitations. The complete